Now, let's just quickly check, does this make sense of what you observe? Okay, get your calculator out for a second. You got your calculator there? I want you to try out a number, like say, well, what radius would you like to try? A simple number. How about, I'm going to go even smaller than that, like right at the beginning of things, right? What about when you first started putting air into the balloon, okay? What about when, I'm not going to put in r equals 0, because then I'm dividing by 0, that's a bit of a downer, okay? Let's try something nice and small, like r equals 1. If you put r equals 1 into here, what number do you get out? 5.57, okay? I might write that down, that might be handy for me. When r is equal to 1, dr on dt is 5.57. Okay? So that's what happens when you study. Now, is that fast or slow? Well, I don't have much of a handle on it. Let me see if I can compare it to some numbers. Let's see what happens once the radius doubles, right? Well, you've got the same equation down here, the same formula you can pop your value into. What value do you get for r? Sorry, dr and dt, I beg your pardon. 1.39. Okay, now just pause before we put in another number. What's happening? Well, the balloon is getting bigger, right? The balloon's getting bigger. It's gone from 1 centimeter radius to 2 centimeters radius. But what's happening to dr and dt? It's slowing down. It's decreasing. It's slowing down really fast, right? But do note, it's still positive, right? It hasn't gone negative or anything like that. Why is it positive? Yeah, you're still blowing air in. Okay, so it's growing, but it's not going as fast. Let's go one more just for good measure. Put in 3. Okay. What's going to happen once the radius is 3 centimeters? 0 point? Okay. So I think that's enough just to see what's going on. Okay. The radius is slowing down, and that is exactly what you can observe as you go from here, right? Even though my lungs are pretty pathetic, you can see from 3 breaths to 4 breaths to 5 breaths, it barely moves at all, the radius, right? Do you notice that? Okay. But there's huge changes here between 1 and 2. Does that make sense? Are you with me? Okay, good. Let's think about surface area now. I haven't put anything on the board here that relates to that. I rubbed it off before, but I'm interested in dA on dt. Well, how am I going to get to dA on dt? Think about how we did it over here. I'm going to need to combine some derivatives, and you're going to have to help me work out where we're going to get these derivatives. What derivatives do you think would be suitable to combine to give you dA on dt? Think about how we did it before. Any suggestions? dr over dt. So I can combine this, dr and dt, and which other one do you want to compare it with? You got the dt on the bottom. What's going to be up the top? What do you want to be on the top? You want the dA up there and the dr down the bottom. You see that's going to cancel? Is that going to work? So how am I going to get either of these? I know what dr and dt is. I worked that out. How can I work out dA on dr? dA on dr. You can use you actually know a surface area formula for a sphere, right? Now just watch out here. There's something strange and interesting that I'm not going to explain yet. I just want you to notice. The area formula for the surface area of a sphere happens to be 4 pi r squared. Now I've written 4 pi r squared on the board already about 3 minutes ago. Right? But these two things are really different, right? Like that's a derivative, that's a rate of change. This is just, well, it's a size, it's how big the surface is, right? We're going to come back to this relationship a little while later, but for now I'm just going to put it there. Why did we say this formula again? What was the use of stating it? Yeah, I'm after that derivative, aren't I? Okay, so I'm going to differentiate here, which gives me 8 pi r, very good. And this is what I can put into, I don't know why I wrote it over here. This is what I can put into here. dA on dr times dr on dt. Okay, so let's see here. dA on dr is exactly where I want it. It's 8 pi r times, and dr on dt I've worked out over here, right? 35 on 2 pi r squared. Can you do some cancelling for me and tell me what you get? Is it 140?
Yeah.
On, looks like I'll just, on R. All those pi's will cancel. And we all shed a tear for the pi's. Okay, so are you happy there? Does that make sense? Now again, we don't need to write it out here, but I think you can see, because this is even simpler, right? What happens as the radius gets bigger, right? Well, when you start off with like a small value of R, like say 1, okay? The rate of increase of the surface area is 140. That's really fast, right? It's like, whew, it just inflates, right? But as R gets bigger and bigger, right? For example, by the time you get to R equals 3, what is 140 divided by 3? It's like 30 something? 40 something? 44-ish, okay? So it's dramatically decreased. It's still increasing, but it gets slower and slower and slower. So in fact, it's a hyperbola, isn't it? See what's going on? Okay, one last thing. All of this, you can see we've related volume and area and radius. We've also related it to time, but I haven't said anything about any times here. So I'm going to ask you this question. What if I said, can you tell me, let's go back to radius for a second. Can you tell me how the radius is changing after 10 seconds? Now, you've got no formula here which has t as a variable you would insert here. But I wonder if you can work out how we would find out what it is. What was the very first piece of information I told you? The very first one? dV under t, right? dV under t equals 70. Yeah? Now I want you to look carefully at this for a second. Look carefully, because tucked away inside here is the relationship that you're after. Okay? After 1 second, what's the volume? 1 second of blowing, the volume's going to be 70 cubic millimeters, right? What about after 2 seconds? It'll be that, and then it'll go again, right? Yeah, you're halving. You're going back in time. After 2 seconds, it'll be 140. After the third second, it'll be 210, etc. 70, 140, 210, 280. How would you describe that relationship? It's a constant, well, it's not constant actually, it's changing, right? So it's getting bigger. The gradient is constant though, right? So here's what we can do. Remember, we've been using differentiation. The thing you haven't used yet is integration, right? So if you look at this guy, right? Grab another color for this, right? Have a look at this. Can you see with this equation, I can integrate both sides. What do you think would be an appropriate variable to choose? What am I trying to get to? I'm trying to get to a time, right? So I'm going to integrate both sides with respect to t. That gives me this. Like so? Is that okay? Now I know that left-hand side looks a little bit weird. You're like, what's going on with all those dt's? That's okay. You can see it cancels. You're just integrating with respect to v now, right? Because the variable has actually changed. Do you see that? This is just like what we did when we were doing integration by substitution. The variable has changed here. This is still 70. And what are we going to get? V equals, what happens when you integrate a constant with respect to t? 70t. And don't forget, it's all indefinite. So you'd say plus c. Yeah? Now, how do we work out that constant, by the way? How do we find out? What would we usually do to find out what a constant is? You need some kind of value that you can substitute in, and then that cancels everything out. When you were about to start blowing the balloon, what was its volume? Its volume was 0. At time 0, when t equals 0, the volume will equal 0. So in this case, as in many, since v equals 0 when t equals 0, it will all evaluate to c will equal 0, so that there is your equation there. Now you've got a relationship not just between volume and radius, but volume and time. Okay? Do you reckon you could work this out now? I'm going to give you a couple minutes to have a play and see if you can work out a value for it. I will show all of you. I think some of you are sort of on the right direction, but I've sort of intentionally thrown you somewhat into the deep end because I could just give you rules for this, but then you don't feel your way through it, which I think is actually a really important part of learning this. Let me help you out. Okay. We know that V equals 70t. What does that mean? As time increases, the volume increases at a rate of 70 millimeters cubed per second. Okay. So after 10 seconds, when t equals 10 for 10 seconds, when t equals 10, the volume equals 70 times 10. Are you okay with that? So it's going to be 700 cubic millimeters. Okay. Now, I know how to work out dr and dt if only, have a look at my equation for dr and dt over here. Here it is. My equation for dr and dt at the moment, it is in terms of r. Do you see that? So if I know what r is, if only I can find out what r is, I'll be able to pop it into this equation. How do I find out r, the radius, if I know the volume? Yeah, there we go. There's the relationship between volume and radius, right? So I can say that's 700. That 700 is 4/3 pi r cubed. That's what it's equal to. Okay, so r cubed is just going to be 700 divided by 4/3 pi, whatever that happens to be. The radius you actually want, therefore, is just take the cube root and you'll have some weird number, but that's okay. This is just a workout for your calculator, really. Okay, once you've got that radius, whatever it happens to be, you can pop it into here. Does anyone have a number for it yet? Can someone tell me their number once they get to it? When r is that terrible mess, what does dr and dt actually end up equaling? Can someone give me a decimal? A couple of decimal places of accuracy, maybe? What do you got for me, Paul?
Oh, okay. Yeah, that would be 0.1836.
Okay, now let's just do a quick sense check. Does this make sense? 0.1836. That's quite low, isn't it? You expect it to come in sometime after this? Yeah? Well, that does make sense. The rate of increase of the radius drops off really fast, right? And if you're going after 10 seconds, yeah, it only went fast at the beginning and then it slows down quite quickly. Okay? Slows down quickly.